Okay, so here's another example for class 11. This is example 2. And we have two smooth spheres, A and B, and each has a mass m, right? So I like to actually put in some values for this right here. I think this is a problem that doesn't have any mass values or velocity values, but I decided to give it some. All right, so if A is given a velocity of VO, well, this B is at rest, determine the velocity of B just after it strikes the wall. The coefficient of restitution for this is E, so I'm going to put some numbers into it. So I use the following values. I have 3 meters per second and a collision or a coefficient of restitution between everything is going to be 0.8, right? So, well, and then I also want to find the efficiency of the collision, right? Or maybe even the collisions. If I can, I'll make this a little longer, this video. So this is a long problem actually. So this ball A is going to strike B, right? It's going to cause A might bounce off a little bit, but it's going to cause B to move over. I guess it's going that way, right there, towards the wall, and from the way that you're looking at the thing. Then it's going to strike the wall, and it's going to bounce off. This is so this is a problem where we introduce when we have an immovable object, right? So we need, this is an important kind of concept, like how do we handle the immovable object, because its mass is infinite and its velocity afterwards is going to be 0. So we have a little bit of a dilemma. So we're addressing that right there. So we have several things. We're going to try to have this chain reaction type of thing, and then we're going to investigate what do we do if we have an immovable object like the ground or a wall. Okay, so I start out, so I'm going to do this in two parts. A hits B, and then B hits the wall. So I would really like to know what B's velocity is going to be after it strikes the wall. And we could even go crazier. We say, well, no, B, then like if A kept on moving, now B is going to hit it. Just, and like, where is it going to hit it? We could play around a lot. Let's not do that just now. Okay. And by the way, all these things are instantaneous that are taking place, even though we couldn't figure out the acceleration from this right here. The acceleration deceleration is like happening really quickly during these impacts. We just kind of try to ignore that little instance. So we have like pretend it's instantaneous. So let's do this first part here where the A hits B. So it's very similar to what we just did right here. Here's our initial in example 1 we did this right here, and then we have impulse. I wrote imp on this one, and then we have final. So you can, there's a weird way to write final. I have impulse into here. So we have this guy right here is M A, and all M's are equal to each other, so they're all going to cancel out, but it would be a little bit more interesting if they didn't cancel out. So we have our little impact thing going on right there. And then after the fact, because we don't know if A is going to bounce back that way, so we'll go ahead and assume here. So we got MA, VA2, MB, VB2. That's taking place. So in the x direction, which is obvious because there's only the x direction here. Let's see, we meant to put our diagram pluses and equals in there. We're going to say MA VA1, nothing happens. It's going to be equal to MA VA2 plus MB VB2. All of these masses are the same right here. So what we're left with right here is this is equal to 3, I've decided, and VA2 plus VB2, and that's going to be our first equation that we have in here. Now we use the coefficient of restitution to try to establish here what their other relationship is, because we have two unknowns in one equation. So we have VB1 minus VA1 divided by VA2. Oh, look at me making a mistake. It's the relative velocity after on top okay, and we know that we decided that's going to be 0.8. So we have VB2 minus VA2 divided by VA1, but this is 0 right here, right? So it's easy enough to look at this and say that we have, and we know this value, we know that value is going to be 3 in the positive direction. So what we can say is VB2 minus VA2 is just 3 times 0.8, or 2.4. Right there, right? So that's our second equation. We solve 1 and 2. Not too difficult to do. And we get VA2 is equal to 0.3 meters per second. So it still is going in a positive direction. And VB2 is 2.7 meters per second. So it didn't exactly, there was something lost that was in between those two things right here. So I say, let's figure out the efficiency of this operation. So we're going to say that we have kinetic energy 1 plus potential energy 1 plus the work that's done in this one, and that's really going to be, these are really going to be losses, and then we have the kinetic energy and potential energy afterwards. Now both of those are 0. We're not actually going to solve for these losses, although we could get them. We do 1/2 mv(a1) squared plus, or I should say minus losses. It's going to equal to 1/2 mv squared, 1/2 mva2 squared plus 1/2 mvb2 squared. Now we don't know these masses right in here, but we're going to take it as a ratio, so they would eventually cancel out. So let's just figure out what KE1 is going to be, and we could even say this is on a per mass basis. So what we do in thermo is we would write as lowercase when it's on a per mass basis, right? So just 1/2 VA1 squared. So we have 1/2 3 squared, right? 1/2 3 squared. 4.5, and you could say that these are Newton meter per kilogram. I'm going to do it on a per mass basis. And then KE2 is 1/2 VA2 squared plus 1/2 VB2 squared, or we would say, but everybody's like sending me emails right here at 9:05. But so what we have, 0.3 squared plus I got a 1/2 2.7 squared, and so what we end up with when we add them together is I didn't add them together. I put them out separately. So this one right here is actually 0.045, and this one is 3.645, 3.645, and 0.045. I didn't get a sig figs right here. We have 3.69 Newton meters per kilogram. So if you take and you divide those through, we have KE2 divided by KE1 of 3.690 divided by 4.5. We see we have an 82, and it should be something less than 1. Hopefully it's less than 1, otherwise we've just defied the conservation of energy, and we've created energy, which it would be very lucrative if you could figure out a way to do that. But we have it as an 82% efficient collision that's taking place. Well, now let's see what happens when it hits the wall right here. So now we have a second problem in essence. We have B, it's traveling much faster than A, so A is not going to catch up with it, right? but it's traveling at 2.7 meters per second, and it's about to hit the wall. And so we have to kind of like start thinking about how that happens. So let's do our diagram. That diagram helps us to figure out and think through these scenarios right here. Right? So here's this wall. Here is the velocity of B, 2, and now we're going to have impact with the wall right here, and it's going to be now we want to find out what the impulse, what the thing is going to be. Now it's going to kind of pass through the wall, so we just inherently know that it has to bounce back right here. So if we're going to have like here, let's write MB times VB2 plus 0 right here, because we have equal and opposite, the wall is going to push back, is going to be equal to MBVB3, and in fact it's going to be negative right here, plus M wall V wall 3, I guess. Well, this is infinite, and this is 0. When you multiply infinity by 0, what's the answer? It's unknown. You can't multiply infinity by 0 and then hit equals and come up with an answer. I mean, pretty much it's going to be 0, right? So this is, and our answer would be, does the velocity equal the velocity? It can't be negative, right? So this is undefined right here. Can't be done. So we can't use the conservation of momentum here. But what we can do, or we can indeterminate.
Dr. Dio?
So 1 second, I have to pause this video right here. Okay, let me see. Oh, I had a question from my statics class who is taking an exam right now. Okay, so what do? We use the coefficient of restitution. Here's our core taking place, and we say E is going to be equal to, let's take the velocity of B, 3, minus the velocity of the wall, 3, divided by the velocity of the wall, 2, minus the velocity of B, 2, right? And we're going to still assume that it's 0.7. Now, coefficient of restitution can vary depending on what's hitting what. It isn't necessarily only about the ball. It's also about like the wall and how soft or hard the wall would be in terms of its ability to impact something. You can imagine if it was foam rubber right there, it would be different than if it was concrete, right? So, but anyway, we take a look at this. We can see, well, that's 0. And this is 0 right here, right? So we just have VB3 divided by negative VB2. So what we can say here is that we're going to have, remember that this is VB3 and that this is 2.7. What did we get up above? 2.7. I should have put a 3. I should put the sig figs onto there, right there, right? So what we end up saying is that VB3 is equal to a negative 2.7 times 0.7, you end up with 2.160 meters per second. So VB3 is equal to 2.16 meters per second this way. Now, what we also want to do is figure out what the efficiency of this is right now, the efficiency of the wall. So let's figure out what the KE1 is going to be, and well, let's call it KE2 and KE3 right right, is going to be. Now, once again, we're going to do this on a per mass basis, so maybe I should have written that as KE2 and KE3. So we have 1/2 V2 squared and 1/2 V3 squared, and that's a B3 squared, B right there, right? So if we do that, let me see what my losses are going to be. I say, well, here is just going to be 3.645 Newton meters per kilogram. And this is going to be now 2.333 Newton meters per kilogram. So our efficiency of the second one that we had, maybe we could call this one efficiency 1. Here's the efficiency 2 of the next thing that we're going to have. Is it's going to have the output KE3 over KE2 on the thing, or it comes out to 64.0%. So that's an interesting thing to start to reflect on, how that happened right here, right? So that was much more inefficient than this initial one right here, right? So this is our first efficiency that we found when it was ball hitting ball, but now when it was ball hitting wall, it was less efficient. Interesting type of results. 16-minute video.